find the common ancestor of the deepest nodes. Of a binary tree. So in this case, it would return 20. Oh, the lowest.
Okay.
So in this case, if the output will be 20.
If the input's 15 and 7.
The input is the tree. It's a tree node, and the output is another tree node. So the input is the head. The output is the lowest, the common ancestor of the deepest.
Oh, okay. Of the deepest nodes. Interesting.
Yes. Oh, and you can assume that it's gonna be the leaf. How does it this? Each node, either they have zero child or 2 children.
Okay, I see. So they're either leaf nodes or they have 2 children, I guess. Okay, so at first thought, it seems like there's 2 main parts of the question. Like the first part is you have to find the deepest nodes.
Okay.
That doesn't seem very... like, that doesn't seem easy. So I guess you could do a depth first search, and you could keep track of the depth as you go down each recursive call, I guess. And yep, and then you like update a max.
Okay.
And then you could do it again for the second deepest node. I'm like kind of wondering if there's a reason, like if there is some kind of common ancestor for the 2 deepest nodes. Like I'm wondering if that question's different than the lowest common ancestor from any 2 nodes. Like, do the deepest nodes have something interesting about them? Okay, so currently I have like a pretty good idea of how to find the 2 deepest nodes. And from that, finding the lowest common ancestor, I mean that's a bit difficult too. But I think I could do that by So I'm assuming if 2 nodes have the same depth, if more than 2 have a depth of 3, for example, what's the common ancestor? If multiple tie for the deepest nodes.
Multiple ties for the deepest.
Or like there's more than 2. So let's say there's 3 nodes or 4 nodes that have a depth of 3. Not just 2, but there's 4.
Okay, then you return this, right?
Oh, okay. So it's not just 2.
For all the deepest nodes. It's not
Oh,
just.
okay. Could it be 1 deepest node?
What do you think?
I think yes, and then it should just be the node, like like if. Oh wait, but you said that each node has either 2 children or no children, so that's not a possible case actually. In other words, there's at least 2 children at every level of the tree, because you said it's not possible to have 1 child. It has to have 2 children or no children. So I guess that's not a possible case.
Or it's still possible, like if the root does not have any children, then the root.
Okay. For that case, yeah.
Yeah.
Okay, I'm gonna try to think of this as 1 problem rather than two problems.
Okay.
Because, yeah, currently I'm thinking, okay, I could find the deepest nodes, but then I'm like, how do I even remember them? You know? How is that even useful? Like, what am I going to store? The node? I don't know its location. I don't know where it is in the tree, so it's not even that useful to just find the deepest nodes. You know what I mean?
I mean, yeah, but you can try to find the common ancestor of those.
Right. So, like, combining the problems. That's what I think I need to do now. So, okay, but, like, if I'm just going down and I get to this 9, how do I know this 9? Like, there's no way to know if this 9 is one of the deepest nodes.
Right.
Oh, it's almost like I need to do a breadth first search. Aha. Level order traversal.
How do you want to do it?
Okay, well, one of the things I was thinking of, like, depth first search by itself makes things really tricky with this problem, because if I get to this 9, I mean, what do? I don't know if it's the deepest node. I don't,
Okay.
you know? So it's not that useful. But if I do level order traversal, I know when I get to the lowest node. Namely, like, here. Yeah, I know when I get to the lowest one.
Okay.
And so then, I'm thinking, like, if I store it in something like this, so that just helps me find these 2. But there could be more. There could be 4. Ooh, is there a pattern where they're always... Okay, if there's 2 of them, because of the rule that you said where each node has either 2 or 0 children, if there's 2 of them, I know they have to be the child of the same parent. Do you agree?
Okay.
If there's 4 of them, I'm trying to see if, like, certain trees are possible with this 2 rule. So if I have, like, a 5 here and let me just move these over here for a second. This is tricky to draw. Okay, so I was making these numbers up. Yeah, okay, so this is kind of what I feared. If things are separated a lot like this, it's not like even if there's 4 elements here, it's not like I could just go to this row, or it's not like I could go 2 rows up, which is what I was originally hoping might happen. I have to go all the way up to there. And these could be separated a lot.
Yeah. I mean, if you're saying like doing it this way, you can add null pointer in this array. Some kind of indicator.
Mm-hmm. Null pointer. Okay.
So yeah, you know things when things are apart.
Ah.
But even given that, can you tell me how are you?
Yep. I think I know the pattern, because like I was thinking if these two and like maybe the child of these two were right next to each other, you know, like there was another 2 children here.
Yeah.
And like these were the parents were next to each other.
Mm-hmm.
Then that's when I was thinking of that pattern. Then, oh, you would only have to go 2 ancestors up, because I mean that's just the pattern if it's a completed tree. So I'm thinking if I imagine this like nulls, I mean this would definitely be tricky to implement, but imagining that I could get a tree that looked like this would tell me that I would need to go 4. Okay, wait, never mind. This is 1, 2, 3, 4 levels up, which doesn't make sense. Okay. Yeah, I don't see the pattern right now of how many levels to go up.
Right. I mean, I can imagine some kind of recursive call, being like you're always going up until this has a common ancestor, which in this case is the 5. Right?
Mm-hmm. So like a recursive level order.
Yeah, or just like a while loop. Like while their next level ancestor are not the same, you keep going up.
Oh wow. But it's... Oh, I see. And you could tell which ancestor's which because like well, actually no, it's tricky. At least in this array representation. How do you know that the...
I mean,
20 was the parent and not the 9?
you have no null after we complete it. And then all the child, their index divided by 2.
Right.
Yeah, something like that. And then -1 maybe. Like, oh no, actually, just minus divided by 2, and then this would be 2 divided by 2. This is 1. This is 3 divided by 2. This is 1, 2. Then you have the index.
Mm-hmm. Yep. Yeah, and maintaining these nulls I'm pretty sure because of that rule that you said where it's either two, it either has two children or no children. Well, okay, now I'm blanking out. Like, what if you had this though, where it was like, this is the part that kind of scared me a bit with maintaining that array. Like, what are you just gonna? Are you gonna fill in more nulls here?
I mean, yeah, in the solution.
So you're supposed to fill the nulls all the way down?
Yeah, in the solution.
I see. I see. Oh, and then you could even put in the queue, you could actually put a null there.
Yeah.
Okay. Okay. I see. Yeah, that was the part that I was like not so sure about, but that makes sense.
Okay, but okay. Yeah, I think we're good with the solution.
Yeah.
There is another solution where it's much. Yeah. Is there any other solution? Yeah.
Okay.
That's not doing those.
Okay. Is it with space, or do you want me to like not have?
Not have space.
Interesting. Okay. Okay. So if we don't have space, okay, I'm kind of thinking of something recursive, you know, where somehow a recursive level order traversal, and you go down. Okay, recursive level order traversal is harder than it sounds.
Okay. Do you want a hint?
Okay.
That's not a level order traversal in the second, because I wasn't thinking about level order traversal, but like you bring it up, and I think it's quite interesting. And yeah, we actually worked out a solution. You know, that's pretty nice.
Mm-hmm. Yeah. I thought you were giving me this because it was like a follow up to this idea here.
Oh no, but it was kind of like
yeah.
kind of related, but yeah. No, it's definitely related since we already like work out a solution that's also, you know, level order traversal sort of.
Mm-hmm. Okay.
But
so
yeah,
if we do maybe like I'll revisit the depth first search idea.
Okay.
So with depth first search, you could remember the depth as you go deeper and deeper.
Okay.
So yeah, maybe once you go to the furthest, as deep as you can, you remember the depth and you remember the number. Or, okay, wait, if you remember the, if you get to the deepest node, what do you want to return? That's the question. Because I do want to keep this all in the recursive. Like, I want to get the answer by the time I bubble up to the top. So, like, what do I want to return here? I want to return maybe the depth. And then if I return the depth, if like both of these children are returning the depth or their lowest depth, then this number could, well, oh, it could, if it returns the depth of these two, then it could go to here. And oh, okay, so let's say the depth is like so it's 1, 2, 3, and 3. So 20 is like, okay, both of my children, both of my subtrees here have a depth of 3. So that means that this is okay. So if it returns 3 here, and then at this point, this node, let me change it to 6. So 6 is like, okay, this side, this subtree on the left had a depth of 3. This one on the right had a depth of 2. They are not the same. So I am... Oh, okay, wait. Not only do we need to return the depth, but we also... We need to return a tuple up the stack. We need to return the current common ancestor, which is 20, and like the number to beat. Or not beat, but also the number... Because, for example, if like down here we had another thing over here... Oh, sorry. That was...
Yeah, I see what you're saying.
Yeah, so then like only here will it be able to compare a 3 from a 3 and 20 and like and 3 and 10 on the right. So that would be at the 5 stack.
Well,
And so then 5 will say, oh, they're both the same depth. So I'm going to return my node because I'm a common ancestor of both of those. So 5 sees these two tuples that it got from its two subtrees, and it sees that they have equal depths on both sides. And so it's going to declare itself, oh, I'm a lower common ancestor of these two. So then 5 is going to return 3, 5. So this is like what the left call got, and this is what the right tree got from 5.
Okay.
Yep. And yes.
Okay. What if this 4 has something like that, and
Sure.
this 4 has, you know, a complete tree as a node here?
Yeah.
That's your child. What would happen?
Okay. So yeah, so 8's gonna get to the point where its left subtree is gonna return like a depth of 3, and I guess the current lowest common ancestor could start off as 3 also. And then the right's gonna return depth of 3, lowest common ancestor 5. The 8's gonna see that its two children have the same depth. So
Yeah.
And then it's like, then it's going to return that depth, which is 3, with itself, like comma itself as the lowest common ancestor. And then by the time we get to this 4, we're going to have the left as being like depth of 3 with the lowest common ancestor of 8 currently. And the right side's going to return a depth of 10 with the, depth of 3 with the lowest common ancestor of 10. And then 4 is going to return 4. 3 with 4.
True. Wait. So what exactly is the 3?
The 3 is the depth of the lowest common ancestor in the left subtree. It like starting from the top. Or maybe it's better to start it from the 4. That might, or like start it from the left side. I don't know, but something like that.
Okay, and then what would... Okay. What will happen once you return to this 5?
Okay. So the 5 is going to see something like still a depth of 3 and 20. That's still going to be the same because that's their common ancestor. And then this side is going to have 3 and 4. And then it's still going to return 3, 5. Because this 5 at this iteration sees that its left and right subtrees both have nodes at a depth of 3, and so it can declare itself the lowest common ancestor so far. It's possible that like up here there's more trees, so yeah, the idea is to just return this.
Okay. Okay. And what happens if the tree given is the root given of the tree is 6?
Okay, yeah, so that's a good question. So what happens is the left side will have 3 and 20, and the right side is going to have 2 and 9. When there's a single thing, I'm just returning itself as the lowest common ancestor, by the way.
Okay.
Yeah. So anyway, the 6, at this iteration, it'll see that the left side and the right side, their lowest thing, their lowest depths aren't the same. So
Okay.
it's just going to return that.
Okay.
So it kind of bubbles up until it gets to the 5, which is then going to analyze this and this. Yeah, because I am thinking about it, like, what if the whole tree was just 6 down to that?
Okay.
Yeah.
Okay. So what will be the space and time complexity?
Okay, so since this is like a recursive stack, so I guess time complexity O of n, because we have to go through all the elements, and space is O of 1, unless you include the stack space too.
Can you implement it?
Sure. So def of, let's call this what was common as O C A of deepest nodes. Yep. So I'm gonna have a DFS function within here that's going to take. What is with the spacing here? 1 second. Single. Oh, what? Wait. Let me just copy some of this text so that it looks better. So LCA of the deepest nodes. Okay, so sure, if not root, return 0 or something. Well, actually, yeah, okay. So now I'm also gonna make this recursive function. I'm wondering if, yep, I do not need to, you know, instead of doing, the depth from the 5. When like we're at the stack, I'm going to analyze the depth from 4 and then add 1 to that when I return it to the stack above. You'll see what I mean, I think. Because in that way, yeah, all I have to care about is the root. I don't have to pass in, well, yeah, okay, whatever. So left is going to get DFS of root dot left, and then that is hopefully going to return something like that, DFS root dot right. Okay, so now that we have something that looks like this, the idea is that if left dot, or if left at 0 equals the right at 0, so if they both have the same depth, then I can confidently return, so here's what I was saying with the depth. I'm gonna increment the depth by 1, and then I'm gonna put myself as the new common ancestor. So this is the kind of tuple, you could say, that I'm returning. And then else, if they're not the same, then I want to return the exact same tuple that I got, but the one with the larger depth.
Okay.
Left 0 is greater than right 0. Return left, else return the right side. Okay. So let's deal with the base case quickly. So if yep, so if not left, and so are we still holding the rule that they still both need to have 2 children or no children, right? Okay, so then this will hold. So if this is the case, then just we are at a leaf node, and I want to return 1, indicating our current depth, and then I want to return our own value. Okay. So that's good. So then what I'm going to do is I'm going to call my DFS function from here on the root, and that's going to get me a tuple. And then I guess I could just return the, we want the ancestor, which is the second number of the tuple, not the depth.
Okay, but that's supposed to be a node pointer, not a value, because it's a tree.
Okay. So in that case, then this tuple is just going to be the nodes.
Okay.
Yeah.
Okay. And then you're not incrementing the depth in this 2 case?
Ah. Right. Yep. Yeah. Left 0 plus 1, left at 1. Yep, makes sense. Okay. Yeah, I think this follows the logic that I said pretty well.
Okay. Can you go through the exam pattern?
Yep. So we will start at 5. So DFS will start at 5, and then we'll go the left and the right side. So Okay, let's go all the way left to 15, right? So we took it all the way to the left. Now 15, at node 15, we're going to return 1 and 15, indicating the current depth and the node. So then let's jump to 20, and let's assume that 20 got something from the left and from the right. Great.
Yeah.
So it so happens that both of these depths equals 1. So what we're going to return here is 2 and the current root, which is 20, which is what I wanted at this point. Okay, so let's jump to 6 here. So 6, when we're at 6, is the root. Then the left and right are not going to be equal because the depth on the left side is currently 2, and the depth on the right side is currently 1. And the left is greater than the right, so we are going to return 3 and 20. So, oh wait, no, not 3. It's, oh yeah, 3. 3 and 20. So now we're at 5. And we can assume that 5 has something like 3 and 4 at this point. And so both of those have the same depth. And so we will return 4. Wait, so is the depth here, would you count this as 4 or 3?
It doesn't really matter, I guess.
Okay. So then we'll count it as 4.
Okay.
Because then 5 is going to return 4. Yep, and then the common root is going to be updated to 5.
Okay. Yeah, that's. And what will be the? Oh, did I ask it already?
Yeah, O of n time O of 1 space.
Okay.
Sweet.
Yeah. Nice.
All right.
Yeah.
Cool.
No more questions.